Hi guys, welcome to this set of videos, and what these videos are going to do is they're going to follow along with the notes that go with Chapter 3, Section 1 out of your guys' textbook here in our Algebra 2 course. Now what we're going to be doing here in this section is we're going to review with you guys solving systems of equations. This is something you would have looked at in Algebra 1. We're just going to review it here in Section 1 of Chapter 3. Before we get started, let's go ahead and give you guys some objectives or learning targets. These are the things you should be able to do or know how to do by the time we get to the end of this set of notes. So let's highlight them for you here. First, you're going to need to be able to solve a system of linear equations graphically, and that just simply means I'm going to give you equations, a system of them, and you'll need to be able to graph them, and from the graph determine the solution for that system. And then what we'll do after we do the graphical solutions is we'll go ahead and take a look at how you solve systems of linear equations algebraically. There's a couple of methods that we're going to want to review that you guys would have learned in Algebra 1. So let's just go ahead and jump right into it. Before we start solving any of these systems, first, let's talk about what a system of equations is. A couple of things. I've got an example of a system for you right here. Feel free to read through this if you need to, but let me pull out the important stuff, and it's this. In order to solve a system of equations, you must have the same number of equations as you have variables. If you have 2 variables, you need 2 equations. If you have 3 variables, you need 3 equations. Okay, whatever the number of variables are. If you have an x and a y, that's 2 variables, you'll need 2 equations. If you have an x and a y and a z, 3 variables, you'll need 3 equations, right? Whatever the number of variables, you must have the same number of equations in order to solve these guys, both graphically or algebraically. So what I've done is I've given you a system, an example of a system of equations. In my first equation, I have an x and a y. That's 2 variables. That means if I'm going to solve it, I must have 2 equations. Here's the other one, also with an x and a y in it. So we would be able to solve this system of equations, and that's why we're looking at this particular note set and this set of videos. How do you do that? One other quick thing I'll mention here before we go to the next page, and it is this. When you solve a system of equations, what you are doing is you are finding the point where these lines, right, because these represent linear functions. If you were to graph them, they would be straight lines. They're linear functions. What you're finding when you find a solution is you're finding the point where these lines cross, if they cross at all. They don't have to, and we'll look at that in a second. So what you're doing is your solution is actually a coordinate point. It'll be a point x, y. You're going to find the solution to x. You're going to solve for y, find the solution for y, and when you put them together, you get an ordered pair. That ordered pair represents where these 2 linear functions cross each other. Where do they intersect? That's going to be your solution, which is exactly what I've got right here for you, right? The point represents where the 2 equations are going to intersect each other. So let's go ahead and take a look at what these equations or what the possible solutions are for these systems of equations. So let's jump over here to the next page. Let me make this a little bit bigger so you can see it. All right, here's what we've got. You actually have three possibilities when it comes to finding the solution to a system of equations, and we're going to go ahead and take a look at each one of these. The first one is going to be the one that you would expect. This is going to be where you find a single solution. It represents an ordered pair, so let me go ahead and highlight that for you. It's going to be consistent and independent, and you will need to know, I am going to ask you for those particular terms, consistent and independent. So just let me explain real quickly what they mean. First of all, the consistent means there is a solution. Consistent meaning there's a point where they intersect. They are consistent. They have a solution. The independent means that they are lines independent of one another. They're not the same line. I have 2 completely different lines. That's the independent part, and then they do cross. They have an intersection point, and that is the consistent part. The second possible solution to get for systems of equations is the consistent and dependent. Consistent and dependent. Well, the consistent, again, still means that there's a solution. The dependent part means both equations are the same line. When you graph them, if you were to graph them, you would get the exact same line. So what the consistent then means for us is actually you have an infinite number of solutions. That's what they tell you right here. Infinitely many solutions. You can pick any point you want to, any point x comma y that falls on the line. Every single one of those points will be a solution. There's an infinite number of solutions because the lines are the same. They're dependent. And finally, our third possibility is inconsistent. Let me go ahead and highlight it for you. And inconsistent just simply means the lines don't cross. All right, there is no solution. Right, parallel lines, no solution. These lines will never ever intersect. They'll never cross each other, and so you're not going to have a solution. Now, when we get to the part of this note set where we're going to be solving these equations algebraically. When it comes to graphing them, it's very easy to see, right? You just look at it. If they cross, you're consistent and independent. If it's the same line, you're consistent, dependent. And if they're parallel lines, right, you're inconsistent. No problem. You have a visual. You can look at your graph and know which one it is. But what about when we solve these guys algebraically, which we'll do in a second? Well, here's how you'll know. If you solve the system of equations and you get a value for x and you get a value for y, well, that represents your ordered pair, where this is your solution. It represents the point of intersection, and you would be consistent and independent. If you solve the system of equations and it all works itself down, all the variables cancel out. The x's go away, the y's go away. If you've got 3 variables, the z's go away. And what you're left with is a true statement. Something like 0 equals 0. Yeah, 0 does equal 0. Or 1 equals 1. -2 equals -2, right? You get a statement that is always true. If that happens, if you wind up doing the algebra and the variables drop out and you're left with a true statement, you're going to be consistent and dependent. Those equations turned out to be the exact same line, and you can pick any point you want to. There's infinite number of solutions. Now, if you do the algebra, the variables drop out, the variables will all go away, and you're left with a statement that is false. This would be something like 0 equals 10. No, 0 does not equal 10. Or you get 1 is equal to a -4. No, 1 doesn't equal -4. That's not true. That is a false statement. It's never true. And what that means is you have 2 lines that never intersect. That's why you're getting a false statement. There'll never be a point where they are consistent. There'll never be a point of intersection. And so there's nowhere you actually have a solution, a true statement. And so that's why you'll be getting a false statement. Now, we are going to look at how to solve these guys graphically first, but the algebra will be coming, and so I want to talk about what we're going to do when it comes to solving these guys algebraically. This chart sort of lists out all of the different ways, and we will use most of them. In fact, we're going to use all of them except for this one. It's Algebra 2. I would never ever recommend setting up a table or chart to try to find the solution to a system of equations. Guessing and checking is a complete waste of time. So I'm not even going to bother showing you how to do it. It's actually kind of ridiculous. I'll never ask you to do it. Fine, they put it in there because technically, yes, it is a way to solve a system of equations. But if you're in Algebra 2 and you are guessing and checking by setting up a table, it's a good thing you're watching this video. There are far better ways to do it, and that's what we're going to spend our time working on. First, we're going to go ahead and take a look at graphing, which they also have down here in the chart. Then that's the graphing way. You're looking for the point of intersection, the same line or parallel lines, and we'll get to that. Second, we're going to take a quick look at substitution. Substitution, I'm only ever going to use substitution in a very specific case. And in fact, they tell you what that specific case is right here in the chart. I'll remind you of it when we get to our substitution example. The rest of the chart is going to be elimination. By far, 90% of the time, you are going to use this method, elimination, to solve your system of equations. So with that, I think we're ready to solve some systems of equations. Head on over to the next page of the notes, and I'll meet you guys there.